Hello everyone, welcome back to my YouTube channel. I am Manoj PS from Sri Venkateshwara College of Engineering, Bangalore. My USN is 1VE23 IS027. I am pursuing 4th semester of BE from the Department of Information Science and Engineering. The subject for today's video is Discrete Mathematical Structures and its code is BCS405A. And the topic for today's video is Klein for groups and particular groups. Let's see the introduction. In mathematics, the Klein group is an abelian group with four elements in which each element is self-inversive and in which composing any two of the three non-identity elements produces the third one. It can be described as the symmetric group of a non-square rectangle as the group of bitwise exclusive or operations on 2-bit binary values or more abstractly as Z2 cross Z2. The direct product of these two copies of the cyclic group of order 2 by the fundamental theorem of finitely generated abelian groups. The Klein 4 groups Cayley table is given by the representation below. The Klein 4 group is also defined by the group representation such as V is equals to A comma B such that A square is equals to B square is equals to AB whole square which is equals to E. All nine non-identity elements of the Klein 4 group have order 2, so any two non-identity elements can serve as generators in the above presentation. The Klein 4 group is the smallest non-cyclic group. It is, however, an abelian group and isomorphic to the dihedral group of order 4 symbolized D4 or D2 using the geometric convention. Other than the group of order 2, it is the only dihedral group that is abelian. The Klein 4 group is also isomorphic to the direct sum Z1 plus Z2 so that it can be represented as the pairs 0, 0, 0, 1, 1, 0 and 1, 1. Under component-wise addition modulo 2 or equivalently the bit string 0, 0, 0, 1, 0, 1, 0 and 1, 1. Under bitwise XOR with 0, 0 being identity element. The Klein 4 group is thus also the group generated by the symmetric difference as the binary operation on the subsets of a power set of a set with two elements, that is, field of sets with four elements such as phi, alpha, beta. The empty set is the identity element in this case. Another numerical construction of Klein 4 group is the set 1, 3, 5, 7 with the operation being multiplication modulo 8. Here A is 3, B is 5 and C is equals to AB is 3 cross 5 is equals to 15 which is equals to 7 modulo 8. The Klein 4 group also has a representation as 2 cross 2 real matrices with the operation being multiplication matrix. Let's see the applications of these groups. Number 1 is geometry. In two dimensions, the Klein 4 groups is a symmetric group of a rhombus and of rectangles that are not squares. The four elements being the identity, the vertical reflection, the horizontal reflection and a 180-degree rotation. In three dimensions, there are three different symmetric groups that are algebraically the Klein 4 groups. One with three perpendicular two-fold rotation axis, the dihedral group D2. One with two-fold rotation axis and a perpendicular plane of reflection C2H which is equals to D1D. One with two-fold rotation axis in a plane of reflection and hence also in the perpendicular plane of reflection, that is C2D is equals to D1H. Let's see the permutation representations. The three elements of order 2 in the Klein 4 group are interchangeable. The automorphism group of V is thus the group of permutations of these three elements, that is the symmetric group S3. The Klein 4 group's permutations of its own elements can be thought of abstractly as its permutation representation on 4 points, that is V is equals to null set, 1, 2, 3, 4, 1, 3, 2, 4 and 1, 4, 2, 3. V is a normal subgroup of alternating group A4 on all four letters. It is also a transitive subgroup of S4 that appears as Galois group. The other representations of these groups are as follows, and the pictorial representation is given. Next application is algebra. According to Galois theory, the existence of the plane 4 group explains the existence of the formula for calculating the roots of quadratic equations in terms of radicals as established by Lodovico Ferrari. The map S4Z S3 corresponds to the resolvent cubic in terms of Lagrange resolvents. In the construction of finite rings, 8 of the 11 rings with 4 elements have the Klein 4 group as their additive substructure. The R power x denotes the multiplicative group of non-zero reals and R plus the multiplicative group of positive reals. Then Rx cross Rx is the group of units Rx cross Rx, and R plus cross R plus is a subgroup of Rx cross Rx. The graph theory. Among the simple connected graphs, the simplest that admits the Klein force group as its automorphism group is the diamond graph shown below. It is also the automorphism group of some other graphs that are simpler in the sense of having fewer entities. These include the graph with 4 vertices and 1 edge, which remains simple but loses connectivity, and the graph with 2 vertices connected to each other by 2 edges, which remains connected but loses simplicity. The next application is in music. In music composition, the fourth group is the basic group of permutations in the 12-tone technique. In this instance, the Cayley table is written as follows. Thank you for watching my video.